In our previous discussions, we have discussed pulse code modulation, that is PCM. And for PCM, we have noted that it is not very bandwidth efficient. This is because the bandwidth of PCM, that is BT, that should be greater than or equal to n, which is the number of bits, time the bandwidth of the message signal, which is BM, right? So it is not very bandwidth efficient. So we need schemes which are less constraining on the bandwidth. So this is our first motivation. And the second motivation is regarding the nature of the data that we need to encode. So concerning the nature of data, we have a couple of examples that would identify some of the laggings in this pulse code modulation. So let us first look into an audio waveform. This picture is taken from an earlier simulation setup mentioned over here, and therein we had an audio signal which was sampled at more than the Nyquist rate. So if we use pulse code modulation, so we would need to quantize all of these samples, right? And for that we would need a large quantizer. That is, for PCM we would need L to power n, so we would need a high bit quantizer. But you can observe that the difference between the samples is very small. So we need to come up with a scheme in which, rather than sending the information for all time periods, we send another relative information, for example the difference between the symbols, right? So in short, the PCM is not very effective, or rather not very bandwidth efficient, because of large n, due to which our transmission bandwidth increases. So in short, there is very small variation in between the symbols. So this kind of a behavior is also seen in an image signal available on this link, and over here you can see that the variations between different pixels is very small. For example, if we take this pixel and if we compare it with this pixel, the overall difference will be very small. So if we consider difference between the two pixels or the two samples in audio signal as a metric, we can significantly reduce the transmission bandwidth, as well as we can improve the SNR. So this discussion leads us to a solution which is differential pulse code modulation, or simply DPCM, and some of its special cases. So in short, we go for the difference in successive samples rather than the sample values. So we go for the differences rather than the sample values. In our previous videos, we have mentioned that the quantization noise is simply delta V square by 12, or this is equivalent to MP square by 3L square. And hence, if the value of MP, that is the peak value of the message signal, which over here is this one, so if this increases, the quantization noise would increase, right? So by taking the difference, we are saying the difference will be much smaller than the peak value. So if we take the difference between this symbol and this symbol, so the difference will be very small, and similarly for these symbols it will be very small, right? So if we can somehow reduce the numerator, we can reduce the quantization noise, and this is going to play a role in our SNR, that is signal to noise ratio, which is simply the power of a signal divided by power of a noise, and the power of noise is mentioned over here, right? So rather than the peak values, right, in DPCM we are interested in the difference D of K. So briefly speaking, the overall SNR improvement from PCM to DPCM, that is differential pulse code modulation, is simply in terms of a gain, which is equivalent to power of the message signal divided by power of the difference signal. And for most of the audio signals, we can have up to 20 dB increase in the SNR. So we have in short SNR improvement by using DPCM if we are considering a voice signal or simply an image or a video. Now let us look into the operation of DPCM. So there are a couple of models for DPCM. The first model is the simpler one. So in this model we have an input which is mentioned as x of k. This is fed to a summation block. Next we take a thread from the input and delay it by a sampling period ts, so that if we have xk over here, so after passing through the delay of ts we would have x of k minus 1, the value at the previous instant of time. So the addition and subtraction yields the difference signal which is d of k, and then in this model, which is the first model, we quantize this difference. So this is a uniform quantizer. So we quantize this difference and eventually we get dq of k. So dq of k is the quantized version of our difference signal. So while rest of these blocks are quite straightforward, so we have sort of a predictor over here which is a delay unit. And what is this delay unit? This is nothing but a transversal filter. And in this filter we have an input. So this input is fed to cascaded delays which are then multiplied with some coefficients a1, a2, al, ak and so on, and eventually they are summed up at the output. So presently over here what we are doing is we are just taking one delay, right? So we are setting the value of a1 equal to 1 while we are setting all other coefficients equal to 0. So we are simply having one delay, so a is equal to 1. So this is why we are having xk minus 1. So to have further insights, let us move towards one simple simulation using MATLAB environment. So over here I have an editor of MATLAB. Note that the code that I am presenting over here is available in the description of this video. So in line 3 I have cleared the workspace, and in line 4 this is just simply a pseudo random generator, so that when you are reproducing the results you will have the same results as mine, right? So I have set the variable k, which is a time index, as over here, and I have set the value from 0 to 10. So for the input I have randomly generated a signal which is basically a column vector of 11 elements. So next, in figure 1 I will use a stem plot to show our signal x of k. So until line 14 let us run the simulation. So this is our figure 1 and this is our input signal which is x of k over here. Note that for simplicity only I have used a random generation for the input. Otherwise for an audio signal or for an image signal you can use audio read or IM read, right, image read, and then you can perform the similar set of simulation. So on the transmitter side we have now the input which is over here, x of k in line 9. So next what we need is we need a delay of that, and for that delay on line 18 what I have used is I have cascaded xk from 1 to n minus 1. So I have discarded the lost value, so it is n minus 1, and initially I have fed a 0 value. So overall the length of xk delay, which is xk minus 1 over here, and the input xk are same. So in figure 2 let us plot the discrete decay. So this is our difference signal. So this was our original signal, and over here on figure 2 we have the difference signal. Note that for some of the values the difference is quite small as compared to the original message signal, but since this is not an audio or a video file, so we will have some samples for which the difference has actually increased. So this difference decay is represented over here in figure 2. So next we have to pass it through a quantizer, and for that I have used a 2-bit quantizer such that the number of levels L, which is equal to 2 power n, this is equal to 4. So we have 4 levels of quantization. So the logical 4 values can be at 1.5, 0.5, minus 0.5 and 1.5. So what we need to do is, if we have a uniform quantizer, we need to approximate all of these amplitudes to one of the four values, that is 1.5, 0.5, minus 0.5 and 1.5. And for that I have used initially a for loop and then an if else statement. The for loop is basically giving us the increment values starting from 0, 1, 2, 3, and the 11th value is appearing at 10, right? So in this loop we will have all the values. Next, in the first condition, that is if the value of this difference d of k is greater than or equal to 1. So over here, if it is greater than or equal to 1, so if it is more than this, so this has to be approximated to 0.5. This is given in the first condition. So if this is not met, and in fact the value of difference is greater than 0, so for the second condition, if the value of this difference is greater than 0, then it would be considered as 0.5. The third condition is if the value of difference is greater than minus 1, so it should be approximated to minus 0.5. And lastly, if the value is less than minus 1, so that is if it is less than this value, so it should be approximated to minus 1.5, right? And I have stored all of these values in terms of an array over here in line number 41. Again in figure 2, where I have put the hold on command, so let us plot the quantized value. So the blue circles are indicating d of k, whereas the green circles are indicating dq of k, that is the quantized value, right? So this is approximated to over here, and similarly all the blue curves are approximated. Thus all of these samples are quantized. So the green signal is output of this quantizer, which is over here dq of k. So this transmitter would transmit this dq of k over the channel. So this is our receiver block for the DPCM, and in this block the quantized difference will be fed to the summation block, and output of the summation block is our estimate of the original input signal, which is over here. So x hat of k is simply an estimate of the input signal x of k, right? So this estimate x hat of k is passed through a delay as in the transmitter side, and the delayed version, that is x hat k minus 1, is then fed to the summation block. So coming back to the simulation and on the receiver, so we have a predictor which is mentioned over here as a delay, or simply x hat of k minus 1. This is labeled as a predictor, right? And x hat is simply x hat over here in line 50, right? So on the receiver side, and in our first sample, we will consider that the value before that sample is 0, so we'll set this value equal to 0. So this is why we have set the predictor equal to 0, right, initially. And then we're going to set a loop I2 from 1 to 11. This is indicating the total number of samples that we're considering. Next, in line number 54, we have an x index. So this is going to be our instantaneous value over here, right, for a given symbol. So this x index is equal to the value of a predictor plus the value of our input, which is dq of k, or simply dqtx that we have labeled. So next, in line 56, I am storing all these values in an array. So as the index value of this loop increases, the predictor would have a previous value of the index. So this estimate x of k is then plotted in figure 3. So here in the red colored circle would indicate the original signal, whereas the magenta color circles will indicate the estimated recovered signal, right? So let us proceed further with the simulation. So again, the red circle is our original signal which was available over here in the input, and the magenta circle is available at the estimation or at the receiver side. So all the processing, after the processing, there are some losses which has been incurred, and these losses are due to an accumulation of quantization noise. So next, in the simulation, let us look into the behavior of our quantization. So for that, in 68, what I have done is I have taken the original symbol, that is x of k, and I have subtracted the x hat of k, and finally I have plotted it. So you can observe the pattern over here that the noise is basically getting accumulated, and similar kind of behavior can be seen over here, that the noise can tends to be accumulated. So this brings us to the conclusion that the DPCM in model 1, this has certain problems. The first one is that the accumulation of quantization noise is there. So in our simulation, specifically if you look into these symbols over here, so over here you can observe that we have approximation upward, and again approximation upward, right? In 4, 5, and 6. So in 4, 5, and 6, in terms of the quantization error, we have an accumulation of quantization noise, right? And then in the 7th sample we have down quantization, right? And again in the 8th we have down quantization, and also in the 9th we have down quantization. So over here again the quantization is having a linear behavior upward. So if we have successive up quantizations or we have down quantizations, we are going to see this kind of patterns which are not desirable. Hence we have an accumulation of quantization noise. The next problem with this one is it has a bad performance in transmission error. This is because since we are working on the difference, so if there is an error in transmission, say because of this channel there was some kind of non-linearity, and the value of this dq of k, say at k equal to 3, got distorted over here. So if this get distorted in DPCM, all of these will be affected because you are working on the differences. But if it was PCM, for PCM you are sending each symbol independently, and hence you would not have that bad a performance. Note that quantizer and the predictor are not playing any role together. So we have to bring this quantizer inside this feed forward loop somehow. And this motivates the next model, which is model number 2. So as mentioned, we have a quantizer here inside this feedback mechanism. So starting with the input, which is x of k, which goes to the summation block, right? So we have an output which is gk. So this gk is simply x of k minus xq of k minus 1, where xq of k minus 1 is simply over here. And next, at the output of quantizer we would have gq of k, that is the quantized version of this signal g. So hence this is equivalent to g of k plus the quantization noise, which is simply q of k. So taking the value of gk from here, we will have x of k minus x of qk minus 1 from here, plus the quantization noise q of k. So if this adds with x q of k minus 1, so this x q of k minus 1 and x q of k minus 1 will cancel off, and hence over here you would have simply x of k plus q of k. So you will get the original signal x of k over here plus the quantization noise, which is not avoidable. So this formulates the transmitter for model 2 of DPCM, and the output of this model will then pass through a channel, and then it will be fed to the receiver. So again at the receiver side, let me rewrite the expression over here, that gq of k is equal to, so this is equal to x of k minus x q of k minus 1 plus quantization noise q of k. So again this expression is written over here. So hence we will get this as the input of a receiver. So for initialization, if we set the value of k equal to 0, so x hat q of minus 1, so this will be a value which is not in the range, so we can consider it to be 0. and eventually we would have simply x of k. So hence, after passing through a channel which is not inducing any non-linearities, right? So we have x of k minus x q of k minus 1 from here plus quantization is q of k. So what we need is we need simply x q of k because this was equivalent to x of k, that is the input, plus the quantization noise. So we need this one to be equal to x hat of k plus some quantization noise, right? So once we get that, we have an estimate of our input signal. So for this we again replicate this block over here in this summation. So whatever is over here is again repeated in this block. So therefore in model 2 we will have a more accurate estimate of the input signal. This is because the quantization is now inside the feedback system. So as a summary, the quantization noise is minimized using the model number 2, and still for the second problem, that is because of the transmission errors, we will still have that problem to a less degree as compared to our first model, but the performance would still be much degraded as compared to PCM. But on the bright side, we have now saved on the bandwidth and increased the SNR value.